the survival distribution topic. So the survival distributions, as it comes, like it sounds like a distribution which calculates the probability of not meeting death. So that we call the survival in here. So you might have covered these kind of topics during another specific course designed to survival analysis, which is coming under medical statistics mostly. But in here, we use some of these concepts, not as deep as those concepts in the survival analysis course, which is designed to discuss about many things in medical statistics. So in here, we are only interested in a particular event, which is death in this case for life insurance. And we will only use some of those concepts which are developed for actuaries to calculate the survival probability. And eventually, if we know the survival probability, we can calculate the death probability, because if you meet death, so that is the event. If you are not experiencing the event, so then it is the complement of event, which is the survival event. So we have only two events, and the event or the death can be distributed in the timeline in different ways. So it can be deferred, like, so for an example, someone can like buy an life insurance product. So, but in that contract, they might have kind of a term that, so you buy your you can buy your insurance contract at this moment, and you don't have to pay anything for the first year. But after the first year, you have to pay monthly premiums of, suppose, 10,000 for the next 4 years. And after the 5th year, which means after your last premium payment, so your coverage will start and it will be valid for the next 10 years. That means your coverage periods starts from 5 years from now and goes for the next 10 years, which means if you are in present, so you don't have to pay for the upcoming year, but for the following 4 years you are paying, and after that you don't have to pay, but you can expect a death benefit premium company based on the benefit they have defined according to your like the payment scheme. So that means in that particular example I explained, so there is a deferred period of 5 years for the benefit, because within the first 5 years, you don't get any benefit, you just have to pay. But even your payment scheme, within the first year, you don't have to pay. So that is the deferred period for the payments. So which means for the payment scheme, we have 1 year deferral period, but for the benefit scheme, we have 5-year deferral period. So that means you can now get an idea that even for the payments, we can defer it to different timelines, and even for the benefits, we can move it to different timelines. So that means we need the idea of survival probability in different time cases, which means the customer is alive today and they are intended to buy coverage, and now we need to, at the time of purchase, we need to find the probability of this particular person. So we know their age, and we have built a life table from all the population data we have about Sri Lanka, for an example. So then we will have a Sri Lankan life table, and we know that if we select, suppose the age is 45. So if this person is 45 or at this moment, then we have the probability of death occurs, or probability of survival for those kind of 40 years old people in Sri Lanka. And we will calculate respective survival probabilities or death probabilities as the complement for the next year and upcoming year. Likewise, we can calculate the survival probabilities for different time periods. So that is the big picture we are going to discuss in this chapter. So in this chapter, we will first start discussing about this age at the death random variable. Yeah, so let's do it like this. I think if I record this one for the entire 2 hour time frame, it might exceed the memory limit. Yeah, but we can continue it for the next 45 minutes, and after the interval, I will start a new recording. So we will have two different settings for today lecture. So let's continue with this recording for now. So as I mentioned in my explanation about that insurer setup, so I discuss about the event as the death. So now, starting from now, assuming that the customer is wants to buy that insurance contract by now, so we need to find the time to the death of that customer. So it's a random variable because we don't know the exact time. So that's why the randomness is there. So in survival analysis, we will have these exact amounts. So if you are finding a cohort, and you can record their ages, and you can observe their status under different, like suppose you are giving a drug to them and testing the improvements against particular disease. So you can record if your like subjects are having like different ages, you can record their ages and start observing them for 10-year period. And then you can say if someone dies in between that 10-year period, you know the exact death time. But if someone survives up to the 10-year period, you know that that person has survived 10 years, but you don't know when will be the death for that particular subject for that experiment or the observational study. So likewise in here, we are not going to observe anyone when we are selling a contract, because the person wants to buy the contract at the moment we are contacting them. So that means based on the previous cohort studies, so we need to find kind of a distributional function and find the probability of death for that customer and decide a suitable premium for that policy, which has kind of a predefined benefit for that customer. So then this age to death random variable is the most important measurement to discuss in this matter. So it starts, so we know that when our age has an absolute 0 value. So which means we don't have any age when age is equal to 0. It's an absolute 0. So starting from 0, we grows, and so age goes up to some point, and we have death at some point. We don't know that much. So from 0 to the time of death, we have a length of stay, and we can say that measurement, the length of that stay, as the time to death. So if the death occurs at this point, so we can say from 0 to this particular point of death is a random variable denoted by t for time, and we have a subscript for that t as 0 because we started the measurement from 0. So this t0 expressed for the time to death random variable as this. This is the time taken to the death of a newborn baby because the age is 0. So that's how we interpret this. So now you might have a question. So if T0 is there, so then it's probably we can have T1, T2, T10 like that. Yes, of course. So if we have like this T30, so this is the random variable. So it start calculating measuring your age starting at your 30th birthday or during that 30th year of birth. So this is the time taken to death of a person who is age equal to 30 by now. So T30 is that time to death random variable of a person whose age is equal to 30. So T0 is the age of a infant and it's the time to death for that infant. That's how that definition works. So it's a continuous random variable which can take any value from 0 to infinity in definition. But we know there should be a maximum value for that one. So since this is, so life insurance is applied for humans, we don't know the exact, we don't know the exact age, which is the maximum age of expected life for a human. So there are some records that some people had lived for 120 years, so 110 years, 100 years, like that. There are some incidents, but we can have kind of an average value, but we don't know the exact value. But if you are designing an insurance for kind of an electronic device, which is a large machinery, so then we can calculate kind of an approximate maximum age for those machinery. Sometimes it doesn't have to be disabled, but suppose we are using a printing, so we are designing an insurance contract for printing press. So then we know that with the time, the technology will come in, the printing machines will use different technologies. So we can find kind of an expiry date for that machine. If the manufacturer is going to build those machines without any bankruptcy for that company, we can expect after 20 years, they will give you a new machine. So in that case, you know that your insurance should only cover for 20 years, because if it is not defective for the next 20 years, obviously you don't have to pay for any kind of defects, because the company will replace that machine with a new machine. So then the infinity is equal to 20 here, because it doesn't go until it lasts. So it should be exchanged, so it will be replaced with a new technological advanced machine after 20 years. So that is a different case. But in between the 0 and 20, the occurrence of a failure of that machine is random. So then you can use this T0 random variable if you are purchasing a new machine at this moment and you are interested in a defect, in a defect which can occur within the next 20 years, and it is random. And we know that there is some probability of surviving up to the next or the maximum length, which is 20 years. So that is a different story. So if it is for the humans, or if it can be for kind of animals, for an example, for horse racing, you can have kind of an insurance for your horse. So then it's also a living being. So that means you don't know the exact time of death. But in some cases, if you're using that animal only for racing for next 10 years, so you know that I need this insurance only for the next 10 years. So this creature will be replaced after 10 years. So then there's a restriction. But if you're buying a life insurance for yourself, so you don't have any restrictions, but you don't know the maximum lifetime you live. But depending on your income and the nature of your work, you can say, so I just need the life insurance for the next 20 years because I'm going to retire after the 20 years. So I can have a pension fund after the 20 years. So I don't need that life insurance. So then you know, you only need, you don't need to go for a whole life insurance. You will stay with a 20-year term life insurance. So likewise, so this T0 value can be used in different ways, but depending on the time for human beings, the starting point is different. So T0 is for a newborn baby, but T30 is for a person who is whose age at 30 years. And their time, the the measurement time will begin at age 30 for T30, and in T naught, it begins at age 0. So that's the clear definition I can provide for this random variable. And then, as I mentioned, so literally it can go to infinity, but we know there has to be a limit. So sometimes we denote that limit with omega. So this is come with an assumption. For some examples, you might have seen that Japan has the highest expected lifetime for women and men in the world. So that means if a person lives in Japan, so they can expect higher lifetime than a person in a war-torn country or a poor country. So then the expected life for some of these countries in Africa or Middle East, their expected life, or even in South America, so they have a low expected life than a person in a developed country. So that the reasons for that number depends on the healthcare system, the infrastructure they have, the facilities they get from the government or the other organizations to uplift their living standards, and the natural disasters they face throughout their life in their proximity. So based on these things, the life expectancy depends. So if you are particularly designing this the insurance product for one population, it can be Sri Lankans or Sri Lankans in the Western province and Sri Lankan in the Uva province. They have different kind of like qualities, for an example, it says like, it's not qualities, facilities. So they might have different facilities for their life. So depending on those facilities, they might expect different kind of different amount of life expectancy. But we don't see that kind of a significant difference in between the life expectancies for people in one country. But if you are comparing it with two countries, obviously there's a difference depending on their economic state and the public infrastructure they have and the natural disasters of that country, or even the man-made disasters. So then depending on the population you select, you can have kind of an approximate value for omega. So you will see in some questions or even in practical situations, so you will assume that the maximum number of years that a person live in this country is 100 years or 110 years or 105 years. Like that you might have seen, or you will see in future in like insurance reports or any kind of policy documents. So the omega is the maximum expected age for a given population, and it doesn't have any specific value. It depends on the population you selected at that time for the calculation. And then we can so those are the like things that we discuss about this the nature of this age to death random variable. And if we assume omega exists, that means the T naught can go from 0 to omega. So that is the measurement span of this T naught random variable. But if it is T30, it's also 0 to omega. But in this case, so from omega, you have to subtract 30. So we will discuss it in future. But for the just clarification, so in here, suppose this was 100. So then for an infant who is newborn at that time, so we can expect the lifetime of that newborn baby is 100 years. But if you have already lived for 30 years, so then you only expect 70 more years for your life. So that's why it differs. But in notation, if for T naught, it's 0 to omega, but for T30, it's 0 to omega minus 30. So that's a difference. So that's how we can like think about the remaining lifetime of a person. Then, since this is a random variable, obviously it can have a probability density function because it's a continuous random variable. And for continuous random variables, we know we can have a probability model, which is called the density function. So we can, since we are interested in the survival distribution, as I mentioned, the survival, if the survival occurs, the other event is death. And in the distribution theory, the cumulative distribution function gives you this relationship, which is the probability that your random variable is less than or equal to some value. So that value is t in here because it's time. And now for the cumulative distribution function, we use capital F to denote that, but we have to be specific about the starting point. So in here, for a newborn baby, the age is 0. So that's why we use F0t. So that is, by definition, the probability of t naught is being less than or equal to t. So this is the cumulative probability of the remaining lifetime is less than or equal to t. In the general interpretation, this is the probability that a newborn baby will face a death before, on or before, the teeth age or teeth birthday. So that's the general interpretation of this probability. So if you know the cumulative distribution function, then from the distribution theory, we can get the density function by differentiating that cumulative distribution function with respect to t, or with, in here it is t because the random variable is t, and that density function is denoted by simple f 0 t. So simple f is for the notation, general notation that we use for to indicate the density function, and we need 0 as a subscript because it indicates the time or the age of that person. Then there's another interesting relationship which is coming through the complement rule. If the death occurs before the age t, the probability is capital F naught t. Surviving up to t means the we cannot observe the death in between 0 to t. That means the death can occur at any point beyond t. So that is the definition for the survival function. So if someone was to find the survival probability of a person who is just born or the infant, and then that probability can be defined as the probability where t naught is greater than t. So in general interpretation, it says the probability that death occurs beyond t or after t years. So we know that that person was alive up to t years, but after that we didn't know at which point the death occurred. So this one is directly accessible through the complement rule because we know that the maximum value that we can get for a probability is 1. So 1 minus the event, which gives the complement of that event probability. And here it's 1 minus the cumulative distribution function, which eventually gives you the survival distribution or the corresponding probability for the survival value of that from that distribution. And if I recall you the cumulative distribution property, so it starts from 0. So it can start anywhere from here, but since it is age, so it should start from 0 and it can grow and limited at 1. So at infinity, it goes to 1. but start from 0. At the start, it's like the probability of death is 0. But at the infinity, there is a definite death, which means the probability of, so in here it's t naught, and so that means at the infinity or at the maximum value of age, then there's a definite death where the death probability is now equal to 1. So by motivated from that point, we can find the corresponding survival function. So in here, it's a, I should use the other. The function is here, and at birth, definitely we have a good probability of survival. So in here, it's equal to 1, which means we assume that at birth, there's no probability of death, but it decreases with the time and goes to 0 at the infinity. That means at the infinity, we don't have any survival probability. So it is given because it is because of this 1 minus capital F value. So the death probability rises with the age, survival probability decreases with the age. So at 0 age, the survival probability is 1. And also, when the time goes to infinity, the survival probability is equal to 0. The limit at the limiting age is equal to 0, and it is monotonically decreasing. So that means there's no such incident that it can increase at, in somewhere in the midway of a. So the rate of changing the probability can change, but we assume that it doesn't increase at some point. Like you cannot expect it to be going somewhere and coming back. So that's not permitted, or we are not expecting that kind of a behavior for this survival function. But you can see the slope is changing at some point, it decreasing quickly and then again slowing down at the end. So those are the things that we need to keep in our mind when we are discussing about the behavior of this death, or the probability of death and the probability of survival. So now we can summarize what we have learned up to this point, which is we knew if we have the cumulative distribution function, then we can have the density function. And also we have the relationship between the cumulative distribution function and the density function. So it is 1 minus the cumulative function is equal to the survival function. So once you replace this density, the cumulative distribution function with 1 minus survival function, still you can get the density function by differentiating your survival function. But now, after differentiating it, you have to multiply that whatever the value of the function by -1 to get the probability. So that's the first expression or the relationship between the cumulative distribution of death, the survival distribution of that time, and the density function of time to death. And at the same time, so we can have an integral to find that, because we know since it is involving this differentiation in here of the distribution function, So we can say that we can find the rate for a small time interval, which is called, suppose in the definition of the integration. So we always adding, so we have the function value and then we add a small amount of time into that function, measurement of x into that function, and then we get the uh, proportion of these two functions and set that delta of the small value to be 0. So that will give the integration. So then differentiation. So at the same time, we can, if we can differentiate that one, which means we can do the integration to get back that value as well. So then, since it is a differentiable function, so you can say, if you know the density, so we can find the survival function directly, or the survival value directly. Suppose this is the maximum value, and this is the starting value for the random variable t naught, and this is the t where we are interested at the time point. And if the probability is greater than t, which means we are interested in this area of the span. That means if you integrate the density function from t to infinity, or in this case for the maximum value, you will get the survival value. Or if you get this area of the curve and subtract it from 1, eventually you get this area as well. Because we know that the integration gives you the area in between the curve and the x-axis for that function. And being a density function, we know that the total area is equal to 1. So that is coming through the axioms of probability. And in this case, so we can use these two integrals to find this survival probability value. So this is also a possible way of finding the survival probability value. And this density value can have different values depending on the distribution we assume. Sometimes we can assume different kind of distributions depending on the information we have. And also, through the probability calculations, we know that if we want to find a probability of an interval, so which means in here, the time to death random variable of a newborn infant is in between A and B. So this probability is defined as the probability that a newborn infant will survive up to A years, but the death occurs before the B years. So then that means uh, we know that infant have survived. So for an example like this, if that person survives for 35 years, so then A becomes 35. And if the death occurs before the 50 year, the 50th age, so then the B becomes 50th. So that we know our study period is running from 35 to 50, which means this period spans for 15 years. So if you mean to find that survival probability, where we know that the person is a newborn in this at the moment, but we want the survival probability in between the age 35 and the 50. So then we will eventually integrate the density function of time to death random variable from 35 to 40 or 50. So in here, in general, we can say the interval goes from A to B, so that we integrate it from A to B. So the integral goes from the interval boundaries. And since we know, so again, I will recall you another relation for the probability theory. So we knew that this is the probability that T naught was less than T. And this probability is taken from 0 to t, where f naught was reflected. So you can use u or any kind of another random variable difference, because we have used t in here. So we cannot use t inside the integrals. That's why I use tau that here. So it will eventually give you this probability. And using this uh, definition for the cumulative distribution, because we have the density function in here, so you can use that relationship in here. This is integration in between two intervals. That means if you integrate the which means the function from 0 to b and remove the part from 0 to a, still you get the probability of this interval. It's like this. So even for this interval, so you might have worked with the z distribution or the standard normal distribution. So in that case, if we wanted to find the probability between a and b, so it's same as finding the area restricted by a and b and the curve itself with the x-axis. So to get this one, if you get the entire area from the left tail to B and remove the area from left tail to A, so then you have a resultant area which is equal to the area in between A and B. So that is same as in here. So that's why we get this relationship with respect to the cumulative distribution function. But when it's come to the survival function, so it is 1 minus cumulative function or the distribution function. That means if you are using capital F, so it's FB minus FA. But if you are using the survival function, it has to be SA minus SB, because we know that for the survival function, it's decreasing. So you have positive large values when the age is small, and when age grows, the value decreases. So to be a positive value, so you always have to get the survival probability of the smallest age and subtract it from the survival probability of the largest age. But for the distribution, it's on the other way. So those are the things we have to keep it in our mind, which is coming from the probability theory and the axioms of probability. And it's quite straightforward. So that's why I mentioned these things. The new thing we learned is this age at death or time to death random variable. And you will get kind of exposure for this topic, even if you are doing some survival distribution analysis in the courses. But this is enough for the upcoming calculations. So now, yeah, I can get a quick example for this one. Suppose if we have kind of a function, for an example, if we have this function for so we can have it in between this span, then so this is the survival function itself. So you can find some qualities or some calculations using this directly. And obviously you can find, as you can test whether it's a proper function. So you can substitute 0 and 100 and see whether it goes from 0 to 1. Or which means if you substitute 0, it should give 1. And if you substitute 100, it should give 0. That's how it works if you have a maximum age. And then for the cumulative distribution, the expression is this, which means if you substitute it here, you can find the cumulative distribution function. And for the density function, you know that we have to integrate it or differentiate it first in here. And if you had F or simple F integrated, still you can get this capital F, but we are starting from S, so that means we can directly find a capital F than the simple F, or we can get the same value with by differentiating this. So you can find these two functions starting from the S naught value. And also, see the other quality of the survival function was it's like non increasing or monotonically decreasing function. So the gradient is the measurement we can use to indicate whether the function is increasing or decreasing. So if you differentiate this survival function once, like in here, and if it is negative for all the t values, that means it's monotonically decreasing, and that's why expecting that quality, that's why we multiply it by -1 to get a positive density for the function. So those are the qualities that we can think of this particular distribution. And now if you want, suppose if you want to find kind of an like probability for the same example we discussed, surviving 35 years to 50. So in here, we assume that the person is alive at 35, but some point, so death can occur at 35 as well, but right after the, which means immediately after the fulfilling of 35 years. And so this is, if we have a S0 function, which means starting from the birth, so then we know the value of 35, S35 is higher than the value of S50. So you just need to substitute these values in here and get the probability. And the corresponding, the same probability can be finding the corresponding distribution function. At that point, you need to use it like this. So that is how you can do. So once you have this one, you can easily do the calculations. So as a trick, if you are given the distribution function, so we can first find either f naught or the capital F function, or which means the distribution function, or the survival function, and then use those for calculations or probability calculations of intervals. So it's easy to work with. And if I recall some of these qualities of the probability calculations, we know that for a continuous distribution, all these four probabilities are same. So that means depending on the situation, you might have to check whether the distribution of the random variable is continuous. If it is continuous, so then the interval probability is same. So it doesn't matter whether the limits are included or not for that interval, because we are integrating from A to B in these four cases, and eventually ended up with having the same value. So that's the general overview of a survival function. And now we are moving to the next modification of this future lifetime random variable, or age, which means age at the death, or random variable, because I mentioned that. So T naught is the time to death of an infant, and we know in insurance, so mostly we are not dealing with infants, we are dealing with grown-ups if for life insurance, but at some cases, even for machineries, so then we can start at T note, but practically we have to deal with a customer who is at some age. That means the time to age starting from that age. So we don't know that age exactly because depending on the customer, it varies. So 0 is somewhere in here. After X years, customer comes to the company to buy this product. So now we are starting calculating. So this is the period we are worrying about. Starting from this point to here, and somewhere in here, the death can occur. So then that is the measurement to death. So this is the time taken to death of a person who is at age X. And this is called the future lifetime random variable. So this is also starting from 0 because we are starting the counting process from this age and start from 0 and go to somewhere. So that's why for the limiting age, with the limiting age omega, so I explained it even in the previous topic, starting point is 0, but the end point is omega minus X, because we know omega is the maximum lifetime we can expect for that cohort. And this person has already spent X years of that. So that means the remaining years is omega minus X. So that's how it comes in here. And then the survival distribution changes with the notation where S naught or S0 indicated that is the survival function for a newborn. And Sx is the survival function for a person whose age is equal to the X years of age. And so I mentioned that this is Tx, or Tx is the measurement of time to death of a person at age X. So for this person, so this is time to death or future lifetime of a person who is at age X. That means for this person, age at death is equal to X plus Tx. So he has already, so that person has already lived for X years, and starting from X, he will survive for Tx more years. So the final age, or the age at the death, is equal to X plus Tx. So at the beginning, it's kind of bit, you might face some bit confusion, but so once you get this into your mind clearly, so it's easy to work with. So Tx is the future lifetime starting from 0 and goes to the maximum life we can expect depending on the age. And age at death is the future lifetime plus whatever the years that that person has already lived. So this is the age. So when we are dealing with age, you have to be careful. So if someone says that there's a person who is age 51 and who purchased a life insurance at age 30, so that means if that person is alive at 51, so his survival distribution gives like this. So at age 30, he started the life insurance, and the survival probability at age 51 means starting from 30, he has survived 21 more years. So that's how it works. So we always count starting from 30, but the value of Tx start from 0. So though the actual age is 51, for the future lifetime, it is only 21 because he has already covered 30 years of life by the time he purchased the life insurance. So that's the point you get into your mind clearly. And now I mentioned that the functions are, the meanings of the function are same, but the starting points are different for age. So we have to indicate that using the subscript. And this is giving you this probability in here. So in the previous case, this was the probability of that person surviving for T more years. So, which means if that person is 30, and if we are interested the event that that person is survived for next 21 years, that means surviving a person who is at age 30 for next 21 years. So we don't know the exact time of death after 21 years, but we know that for sure that person will live from 30 to 51. So in that case, you will see there's kind of a conditional statement. That person has already survived 30 years and we want him to survive 21 more years. That's how his age become 51. So you can use this T extension and convert it to T naught. So it will gives you probability. So this event, the probability that Tx is greater than T is same as the probability that T naught is greater than X plus T, given that the T naught is already greater than X. So this part says present age is X. And this part says he will live up to yeah, if I use X plus T age. So that's the meaning. So eventually it is a conditional probability. And we know that if we know the conditional probability, so which means inside that we have the joint probability and the event probability, which is given by here. So if we know that the probability of B given A, so it's B and A divided by probability of A. So A is the event which occurs first and B will occurs after A. So you can add the same conditional distribute or the conditional probability definition and write down the survival probability of a person who is at age X, and we are interested in the survival time should be T more years. So this is same as a person uh, who has lived for X years and surviving up to X plus T years, starting from the measurement starts from the birth. So then we can simplify this. So this is, if you get the two sets in here, this for this set, the measurements starts from X and grows X plus 1, X plus 2, like that up to the infinity, the maximum value. But in here, it starts from X plus T and grows. So that means if you, for this set, starts from T and go beyond. And for this set, start from X plus T and go beyond. So T is a positive value. So in here it's X, sorry. So T is a positive value. That means adding positive quantity to X. So we can expect that X plus T somewhere is in here. So the joint is starting from this point. So that's why the resultant joint or the joint set is probability that T naught is greater than X plus T. And in here, it's probability T naught is greater than X. So these are the definitions of survival probabilities for a newborn infant. That means we can use S naught in here. So the numerator and denominator contains two different survival probabilities coming from an infant's survival distribution. And for the denominator, it's directly S not X, because the set starts from X, but the numerator, the set starts from X plus T. So the survival probability is S not X plus T. So now we are clear that if we want to calculate the survival probability of a person who's at specific age, we can use the general or the survival function for a newborn baby and calculate that using the exact ages. So these are the ages. So X plus T is the age at the time event, or we can say age at the event. And this is the age at the selection. So selection is the time that person buys the insurance contract. And event is, it can be like when that person withdraws from the contract, or when the contract is over, or when the death occurs. But since it's survival function, that means we know, obviously, from X to X plus T, there's no any termination of the contract or occurrence of death in between X to X plus T years of age. In this example, it's like the person buys the insurance at age 30, and up to the age 51, that person's still alive, and he still use the same insurance contract. So there's no termination. So if you want to calculate something like interest rates or something using the interest rate, and something for investments or something for future benefits payment, so that survival probability, which means S3021, is valid because he's still using the same contract and he's still alive. So then you can use this calculation. So calculation technique or equation to find that survival probability. So it can be used for any other kind of calculation related to the insurance policy. But keep in mind, so we always assume that that person carries the same insurance contract and is alive by that time. But we are not interested the event after that, the next 21 years. So that means, in other words, this S3021 is also be written as F51 and S0 30. So this is also same as this. So that's the general point of view of this, using these survival functions for the calculations. And if we use the same probability for the density function we used in here, the density function in this example, and if we want to calculate this probability like this, so then I can say 51 over S0 30, and for the numerator we have this one, and for the denominator we have this one. So you can find the probability like this. So that's how it works, and you can see that it's quite straightforward work with. And also sometimes you might have to integrate it first and then use it accordingly. And sometimes you don't have to find the survival function or the distribution function. If you have the density function, you can directly use the integral and find the probability if you are interested. So for this one, so we are interested in surviving, which means that person is surviving in between 30 and 51. So if you integrate this function in between, so if you get this f naught t first, simple f naught t first, and integrate it between 30 and 51, you will get this answer as the result. So you can try it by yourself. So that's the first part of the lecture. And we can move on to the actuarial notations and the actuarial use of these survival functions in the second part. And we can have an interval about 20 to 25 minutes, and you can see you guys on like I think it's 10 o'clock in Sri Lankan time. So see you around 10:20 to 25. So I'll stop recording at this point.